And so our next speaker is David Gross, and the title of his talk will be unveiled in a second. Can I read? Power. I'll get it for you right now. So the title is, here it is. So you need power, that's the thing?
I have power.
So 40 plus 5. More.
I was hello? 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 Yes? Okay, I was hesitant to give a title since the title I chose, my wife said nobody would understand. Does anybody know what this refers to? Feynman! Anyway, wrong. It is the title of Sigmund Freud's most famous book, Civilization and Its Discontents. Well, Feynman might have used the same, might have read this book. Good, I'm sure. However, Freud preceded him. So, I'm going to give you a conservative view of quantum mechanics as I see it, compared with some of what we've heard. But let me first summarize, this actually works now. Let me first summarize the state of quantum mechanics, the status of quantum mechanics, which is the most successful framework we've ever had in physics, I believe. Mostly from the point of view of a physicist, because it works. Also because it makes sense. And finally, because it is extremely difficult to modify. And I'd like to discuss these points, but not in this order. Let me start with it makes sense. So quantum mechanics is about 90 years old. 90 years ago was the culmination, in a sense, of the formulation of quantum mechanics, which, except for some minor well, not so minor, enormous extensions and minor variations of principle, has persisted until today without severe modification. But from the beginning, it was very strange for the inventors of quantum mechanics who grew up in a classical era, as we all do in our intellectual development from infant to graduate student. The transition from phase space to Hilbert space is not easy. I really believe that fundamental concepts in physics take many generations to totally absorb. And that in the case of quantum mechanics, a rather young theory, only 90 years old, there are people around, maybe even in this room, who are 90 years old. It's not that long a time in human history. We still are uncomfortable living in Hilbert space. And they're features of just the statement that the realm of, that quantum mechanics is formulated in Hilbert space without going into all the issues of measurement and interpretation that already exhibit the problems that many of us, that all of us to some extent, as Feynman said, are still concerned, uncomfortable about. And here I'm following the description of a recent lecture I heard in Santa Barbara by Pierre Hohenberg, who tries to distinguish between sort of the kinematical framework, the setting of quantum mechanics, independent of how one describes measurement or interprets reality. So in classical physics, states of a system are described by points in a large phase space, 6n dimensional if we have just point particles moving in three-dimensional space-time. Whereas in quantum mechanics, we describe states as vectors in a Hilbert space or density matrices. So we're going from points in phase space to rays in Hilbert space or trace one positive definite emission density matrices. This is an enormous mathematically different framework for discussing physics and physical reality. In ordinary phase space, observables can be defined in terms of functions on phase space, whereas in Hilbert space we have operators, projection operators, and in general they don't commute. And as Heisenberg first pointed out in his seminal paper, the most seminal paper in quantum mechanics, this is, in a sense, the essence of the difference between quantum mechanics and classical mechanics. Properties of states in phase space can be thought of as subsets of points in phase space. So in particular, in this case, X belongs to the subset delineated by this blue curve. Whereas in Hilbert space, a property is a subspace of the Hilbert space or projection operator onto that subset. Now in classical physics, if we have a state, X, in phase space, or might not be a point, might be a collection of points, properties are either true or false simultaneously. That is what, in a sense, how we assign truth values to properties, to points in phase space, to states of the system. And if we were to discuss measurement, would form our picture of physical reality with a realism of the type that Tony Leggett subscribed to and tried to test experimentally. Quantum mechanics, however, we have incompatible properties, incompatible projection operators that don't commute. And there is a deep theorem, which is due to Bell, Cochin, Spector, that if you try to associate using ordinary logic, and I don't know of any other form of logic, the only truth function that can be defined consistent with ordinary logic to arbitrary incomplete products is, no truth function can be defined that applies to arbitrary incompatible objects, essentially because the projection operators don't commute. Early on in quantum mechanics, von Neumann and Birkhoff tried to modify logic in order to get around this problem. But of course, that went nowhere. The editors of the paper that they sent the journal they sent their paper to didn't know which logic to use in judging the validity of the paper. And in fact, Gleason proved that the only consistent way to define, at best, not true or false, but probability values to states, the probability that a state confers truth on a property A, in other words, that a property A defined by a projection operator has some probability, is the Born rule. This is mathematics. This is the mathematical framework independent of what one means by the kinds of measurements we perform that, as Jim said, we recognize but are rather hard to define or interpret. And this mathematical fact is undeniable. To change these mathematical facts, this kinematical framework of quantum mechanics, you simply have to go to something other than Hilbert space and states as rays in Hilbert space. Very difficult to do. No one has succeeded. Now, the real problem comes is that the Born rule does not define a probability function over the whole space of possible incompatible properties. For that, you need the kind of framework, the type that Jim discussed, a framework of an exhaustive set of exclusive alternatives, a set of projection operators that commute, that are orthogonal, that are exclusive, and encompass the whole Hilbert space. Which means that in quantum mechanics, one can describe a system in many incompatible different ways. You have to choose a framework. There is no unique exhaustive description. This truly bothers people when they go to translate this mathematical structure into what we as physicists do, into measurement, and even worse, into interpretation. And there do indeed remain many interesting questions of measurement and what it is in terms of us, who are quantum mechanical objects and part of the system, interpretation, philosophy, metaphysics, and the classical limit. Mostly we describe things in real life, day to day, in terms of the classical limit, in terms of classical concepts, which in quantum mechanics have to be derived, after all. They're not sacred. They come from a particular limit of macroscopic objects, quantum mechanics. Now, these issues are fascinating, and much progress is being made in understanding decoherence, of being careful in how one formulates what measurement might be, et cetera, and applying quantum mechanics and applying these concepts to cosmology, for example, where we can't get outside the system or perform many experiments in order to compare our probabilities with nature. But most of all, as you all know, these have nothing much to do with what physicists do most of the time, and we can get away with the maxim of shut up and calculate, which is what we've been doing for 90 years with enormous success. Quantum mechanics works. And if it didn't work, of course, we wouldn't be here celebrating its anniversary. And it's really absolutely remarkable how well it works. Not just for the atoms for which it was invented, to understand the properties of atoms, but for molecules, and for collections of 10 to the 23 atoms, conductors, insulators, semiconductors, superconductors. In fact, the stuff that's listed up here is the most successful quantitative theory we've ever had in the history of physics. And it's the most reductionist theory we've ever had. If you think about it, the behavior of atoms, molecules, and even ordinary materials are explainable in terms of a quantum mechanical framework plus the dynamics of electromagnetism. Actually, most of this is non-relativistic to an extraordinarily good accuracy. It can be explained just by Coulomb's law. One parameter being the fine structure constant, assuming, of course, the existence of many, many very heavy nuclei. So this is incredibly successful. We use it as a basis for understanding atomic physics, molecular physics, all of chemistry, biochemistry, life, everything in terms of one parameter within the framework of quantum mechanics. Not only that, quantum mechanics invented for the atom works at down to distances 1,000,000 times smaller, or 1,000,000,000 times smaller, many-body theory or quantum field theory, and now even, it seems, works, we don't see any indications elsewhere, in describing the quantum theory, relativistic quantum theory of extended objects, and maybe dynamical space-time, gravity. Some of the non-trivial effects explained by quantum mechanics, invented just to explain the spectral lines and the behavior of ordinary materials. For example, superconductivity. Weird phenomena discovered before quantum mechanics, and so profoundly different than classical physics that it took 46 years to understand the spontaneous breaking of electromagnetism, which has had an important impact not just on superconductivity, but on the structure of the weak interactions, and continues. The quantum properties of ordinary matter continue to be one of the most, and there'll be more of that in the rest of the conference, I'm sure, I know, is one of the most, continues to be one of the most exciting areas in physics, with new quantum phenomena being developed all the time. In quantum field theory, the quantum dynamics of local fields, of Maxwell's theory of electromagnetic fields, for example, quantum mechanics faced the framework among the rest. In addition to the original theory of electromagnetism, faces its most precise tests, which are truly amazing. The gyromagnetic ratio of the muon has been measured, or the electron. Electron, what? The mu doesn't stand for the muon, but for of the electron has been measured, has been calculated to 1 part in a trillion, and measured, even perhaps more remarkably, to less than a part per trillion with perfect agreement. Even though the only thing that QED, quantum electrodynamics, gives us is an asymptotic divergent series in this fine structure constant. The divergence is not a real conceptual limitation of quantum mechanics, although it's an issue when you compare these things. We understand that the corrections to this divergent series are not captured by the asymptotic expansion, which probably is good until we get to the 137th term in the expansion, by exponentially small terms, which perhaps not in QED, but in QCD are controllable. Anyway, this is a magnificent achievement of fundamental physics, unmatched by any other field in science. And you've got to take this as some very strong constraints on trying to modify quantum mechanics. Whatever modification is imaginable had better not affect this agreement. Not only that, quantum field theory, which contains, in a broad sense, all of the applications so far, microscopic applications of quantum physics, has an enormous range. It was invented to work at the level of angstroms, and now has been extended in the standard model to 10 to the minus 18 centimeters. And as far as we can tell, in a reductionist sense, controls physics out to the edge of the universe, with the exception, well, ignoring gravitational effects, which we'll come to. But what makes stars shine and magnetic fields permeate the cosmos are governed by this general framework. And as far as we can tell, it could extend. There are no limitations built into the theory that cause us to suspect that it couldn't be valid down to the incredibly small Planckian distance defined by Newton's constant. So it really works. And not just for the atoms and molecules for which it was invented, but distances a billion times smaller, where we see the constituents of nuclei and the elementary particles of nature, where we now have a incredibly successful quantitative theory of all the forces that act within the atom and the nucleus, together with the Higgs particle, an incredibly successful, well-tested over and over again theory built on quantum mechanics, built on within the quantum mechanical framework. And in this theory, my favorite, quantum chromodynamics, which in many ways gives us an example. Of course, it's only part of the standard model, which excludes gravity and other things. But it gives an example of what a theory, a physical theory, might aspire to. And I don't believe that this could be possible in a classical theory. For example, no infinities. Point-like particles, elementary quarks, but no infinities at short distances, no infinite self-energies or infinite forces. Furthermore, no adjustable parameters in QCD, ignoring the quark masses, which are kind of irrelevant. And outside of QCD, there are no parameters. There's a dimensionless coupling, but that actually defines a scale of length of the size of the proton. So there are no arbitrary dimensionless parameters that have to be measured. Now, in the real world, which contains much more, there are many such parameters. In the standard model, there are 19 such parameters. And finally, no new physics at short distances or high energies. All of our physical theories till then tend to break down if you push them to shorter and shorter distances because of infinities or conceptual issues. So quantum mechanics works. It does make sense. And it is extremely difficult to modify. Proof, nobody's been able to modify it in 90 years, and there have been a lot of attempts. The simple modifications are total contradiction with experiment. And people talk about modifications. They're not easy. And nobody's been able to. So Steve Weinberg is uncomfortable in ways that I am not with interpretation of quantum mechanics, and has tried over and over to modify it and failed. As he admits, it's almost doesn't seem to him possible. But that doesn't mean everybody's happy with quantum mechanics. There's a guy who wasn't happy and quite profound and understood the difficulties of interpretation, measurement, philosophy from the beginning. So many people think it ultimately will fail or have to be modified some way. Large, complex system, people are disturbed by the Schrödinger cat or analogous examples. Quantum mechanics would say that quantum superpositions of macroscopic states in principle are possible, but it's hard to get one's head around such a superposition. And I've been kind. This cat, well, it's kind of dead. So some people are bothered by the application of quantum mechanics to the human mind. I don't think anyone here is, but Roger Penrose is. Some people feel that the collapse of the wave function, whatever that means, that occurs within the human mind or his friend, is due to some property of the brain. You can tell that I don't believe in any of this. Some people believe that at very short distances, quantum mechanics is bound to fail because of general relativity, our understanding of general relativity, black holes, etc. I don't think that'll happen either. But obviously understanding the quantum dynamics of space-time is a difficult problem, one that is at the frontier where many of us are working for many years now. But I would say there's no real evidence that quantum mechanics fails here. Should. Some people believe that quantum mechanics will either fail or have to be reinterpreted, describing the whole universe. And this is the one place that I have sympathy. And we just heard a wonderful talk by my colleague Jim about attempts to formulate a consistent quantum mechanical or description of cosmology. But the problem I'll come to a bit later, I don't think is, well. So it's very hard to modify. So what we're left with, what really works is, we could say, is a framework which goes quite a ways beyond the original framework, but is a natural extension of it, that of quantum field theory. It's actually even more today. It's not just quantum field theory. Some years ago, we thought that string theory, the relativistic quantum theory of extended objects, was a different kind of framework than the relativistic quantum theory of fields, of point-like particles. Today we understand that they're really the same. If you take a quantum state, which so-called string theory, which really isn't a theory, gives you rules for constructing quantum states in a self-consistent, semi-classical method, and one can show, it appears, that those sometimes are different representations, different dual descriptions of exactly the same phenomena that are described by quantum field theory, the relativistic quantum theory of point particles. These two frameworks are not different. They're the same. All our understanding today of string theory, so-called, is that it is a dual, it exists as a part of a much larger framework, a framework of quantum framework that include strings and branes, extended objects of higher dimensions, field theories, and quantum gravity. So if you ask me, what is the framework of theoretical physics today, I say, I don't know. It's growing. We're realizing that it is larger and richer and more beautiful and more powerful than we thought, and we don't know the boundaries. Well, but you know, that's the present framework we use, contains within it the standard model and all of successful quantitative physics. But all ideas, concepts, equations, frameworks are bound to fail sometimes. That's the history of physics. So where should we look for the threats to quantum mechanics? And I really don't think they're going to come from the focusing on issues of measurement or philosophy or interpretation. The history of science tells us that, once again, the best place to look for the breakdown of your theoretical concepts, your laws, is in nature, experiment. So if quantum mechanics fails, we should see signs in experiments. And over the last 90 years, we've seen enormous number of novel, new, unexpected, strange observations, but no signs of any breakdown in quantum mechanics. Is there any hope of discovering breakdowns of quantum mechanics experimentally? Well, it's very hard to think of them. I would love to hear some ideas. Not those focusing on measurement theory or checking Bell's inequalities and things like that. That's not where to look. It's usually, you should look at new phenomena, new, unexpected. But it's getting harder and harder, as you know. So anyway, for theorists who can't do experiments very well, we mostly focus on Gedanken experiments or toy models. And let me end by briefly discussing 3 places where quantum mechanics, or the framework of quantum field/string framework, could be threatened. One, of course, is black holes, about which we already have heard, and in general, dynamical space-time, but black holes in particular. Another is a few examples of features of that are kind of strange from a classical point of view. I'll discuss that. Non-classical quantum mechanics. Quantum space-time. We're still engaged in trying to make sense, even locally, not to speak of cosmologically, of the dynamics of space, the quantum dynamics of space-time, general relativity, gravity. Quantum cosmology, which Jim referred to. The application of quantum dynamical space-time to the whole universe. And what I call the dynamical principle. In addition to that kinematical description of quantum mechanics that I started with, to do physics, you need a dynamical principle. You need to choose a unitary operator that generates time evolution, a Hamiltonian. And where does that come from? So these aren't testing quantum mechanics. These are issues that we now face in trying to push physics forward that might impact severely on what we mean by quantum mechanics. So black holes is the obvious example. As Hawking emphasized after he discovered the black holes evaporate. If you drop a entangled pair into a black hole, and black hole evaporates, disappears, is information lost. So this was a threat. That was the first time a Gedanken experiment suggested that, starting with general relativity, a applying it in a straightforward manner to a quantum mechanical description of black holes, you conclude, as Hawking did, that time evolution is not unitary, information theory is lost. Information is lost. And then he speculated, as Gerard mentioned, that virtual black holes will be created all the time, vacuum fluctuations. So this cannot be described by unitary time evolution. That's a big Gedanken experiment that threatens quantum mechanics. To my mind, to many of us, this problem has been resolved partly by understanding this larger framework of string field theory using the tools of ADS, in which a theory of gravity in the bulk in the space, which is kind of a box, anti-de Sitter space, negatively curved space, kind of a box where the boundary is not totally undynamical, since light can bounce off of it in finite time, and has a geometry of Minkowski space in lower dimensions. And we now understand that there is, one can describe phenomena in these models, these toy models, within this quantum framework, in which there is a duality between quantum fields or strings in the bulk and operators or dynamical variables on the boundary. Particular best known example is that of the duality between supersymmetric, maximally supersymmetric Yang-Mills theory and string theory in ADS5 times S5. And there's a specific, explicit isomorphism between this quantum mechanical theory in rigid space-time, ordinary quantum field theory, close cousin of the standard model, and string theory in this curved space-time. This has been an extraordinarily productive breakthrough, because it allows us to connect these two different descriptions, dual descriptions, and in particular to address the black hole paradox. Is information lost? Because in this example, black holes are dual to objects that we know about, can create in the laboratory, quark-gluon fireballs. And the dual description of black holes in ADS5 are describable also in terms of quark-gluon fireballs, which can be used to account for the microstates of a black hole and calculate the entropy of the black holes, can be used to demonstrate that the time evolution is unitary. This is. And my hope, in fact, is that in the end we'll understand that black holes are what's called, by some who pursue this line, fuzzballs, totally non-singular objects within string theory, which only have an apparent horizon, and there is, but totally differently, Gerard was arguing, no inside of a black hole and no paradox. No paradoxes. That's yet to be understood in detail. Let me come to the second point, what I call non-classical quantum mechanics. So in our exploration, our speculations about nature and beyond the standard model physics, we've been led to interesting, highly quantum mechanical speculations. One of them is quantum dimensions of space-time, otherwise known as supersymmetry, which in a sense is embedding within the quantum framework quantum dimensions of space-time with anti-commuting coordinates. This is a wonderful conjecture. So far, there's no experimental evidence for it. Could be false. But it is really highly quantum mechanical. I can't imagine classical supersymmetry. In quantum mechanics, we can have a world, if supersymmetry were to be there, in which our basic understanding of space-time would have quantum non-commuting dimensions. Then we have something very interesting in some of our speculations in quantum field theory and in string theory. We have theories with no known Lagrangian. In much of the discussion of quantum mechanics nowadays, for example, in Jim's discussion, he imagines constructing quantum mechanics as a path integral, Feynman's interpretation of quantum mechanics. That's great, but what if you don't have an action? You sum over paths, weighted by the exponential of I times the action in Planck units. But quantum mechanics is more general than that. There can be systems with no such action. And we know examples of that. Little string theory, or there's a 2,0 conformal field theory in 6 dimensions. These theories, a lot is known, M theory and string theory itself, actually. We don't know the Lagrangian, the Hamiltonians, I didn't. We don't have a way of formulating these theories which are related to many theories which are well-defined by all sorts of dualities or dimensional reductions. These theories are very unusual. There's nothing about a quantum theory that says it has to have a classical limit. All the examples we know of quantum theories that work in the real world so far are theories which, like electromagnetism, have a nice classical limit, or at least have a Lagrangian or a Hamiltonian. But that's not necessary. And this is actually a big barrier in all of these cases to making progress. These theories can be discussed sometimes in different limits, or dimensionally reduced to theories which are well formulated in terms of the usual path integrals, but nobody knows how to formulate them ab initio. That's a new feature which might, I don't know, not threaten quantum mechanics, but then there's quantum space-time. The quantization of general relativity, which was so problematic for so many years. And at least at the perturbative level, that issue has been settled to my satisfaction by string theory, which is finite and well-behaved and gives a systematic expansion around semi-classical space-time. Correction, calculable, finite, small, too small, unfortunately, corrections to Einstein's theory. But string theory also suggests that all of the properties of space and time, which are fundamental to the way we think about, always have thought about space and time, in terms of smooth geometries or fixed topologies, or even a fixed number of dimensions, evaporate in string theory. For that and for many other reasons, and the other amazing thing that has come from string theory and from this duality between different descriptions, stringy descriptions or quantum field theory descriptions, is a remarkable, surprising, astounding connection between the structure of quantum states and the geometry of space-time in the dual picture. So in the ADS-CFT simple example of this, the boundary is Minkowski space, ordinary quantum mechanical system. The bulk is ADS space with dynamical space-time, gravity, Einstein's theory for large distances. And as 2 postdocs at Santa Barbara, KITP, pointed out some years ago, there's a fantastic relation between the area of the minimal surface that ends on a region A and its entanglement entropy. This has been extended in many directions, but generally speaking, the structure of space-time, semi-classical space-time in the bulk of this duality is determined by the nature of the quantum states, in particular the entanglement of the states on the boundary. So many of us believe that space-time actually is emergent. It's not a fundamental concept. Gravity, of course, is also then to be thought of, as in the ADS-CFT duality, as an emergent. But how do you do quantum mechanics? We have many examples now of the emergence of space, not of time, however. And understanding what it means for space-time, including time, to be emergent, has got to threaten or to modify what we mean by quantum mechanics. How do we think of quantum mechanics without fundamental time? To explore these issues, my strategy is to play with toy models, so I'm exploring a new class of toy models. I don't have time to describe them. Revolutions in physics. A modification of any kind, serious kind of quantum mechanics, is a revolution. Hasn't happened for 90 years. All of us feel sometime it's bound to happen. But the previous revolutions were associated with the only three-dimensional parameters we need to measure things: length, time, and energy or mass. Relativity, quantum mechanics, and we're still trying to have the final revolution. What's left? We don't need any. There are no other dimensional parameters we could go to, higher. Well, we've already done that. Higher, we've already done that. Stronger fields, we've done that. Where else can we go? So it sort of has to be new kinds of questions, not these old kinds of questions. And some of them have already been addressed, quantum cosmology. A new question that physics never had to address is what fixes the initial state. Slava talked about that. What fixes the beginning of the universe? This, for him, is important. The universe, space-time history has a beginning, a boundary maybe, probably not, and an end. And how do we fix them? What are the rules? This is a new question, not associated with this parameter like c, h bar, or Planck's length. And we never had to face this question before. So to answer this question, well, we might not have to contradict quantum mechanics, but surely it will require, if we answer this question, I think we'll look at everything quite differently. And the other new question we've never faced before in physics is what fixes the dynamics? There are an infinite number of quantum field theories. One of them is the Standard Model. That's awfully disturbing. We have 19 parameters. What fixes those 19 parameters? It's only when we're so successful to have something like the Standard Model we begin to ask that question. String theory so far has given us no illumination. What turns a framework like quantum mechanics or quantum field theory or string theory into a theory that you can make predictions with? What's the principle? That, again, physics has never really had to deal with. It always could look at the real world with experiment or observation and choose one of the theories that is described in the general framework. In the Standard Model, we're not satisfied with that. We want to calculate the quark, lepton, mass ratios, and things like that. So to summarize, I'm perfectly content with a sensible, successful framework of quantum mechanics. But I'm not content with our current concepts of dynamical space-time. Thank you.
I'm sorry, but I feel I have to ask a question.
I expected nothing else, Cecilia.
Thank you very much. You know, you're very kind to Standard Model by saying that it has 19 parameters. Unfortunately, since the neutrinos have been found to be massive, 10 more parameters enter. Okay.
I was very careful. The Standard Model does not contain neutrino masses.
But it
there
could.
are extensions of the Standard Model which have 10 more parameters.
I wouldn't call that an extension. It's
I
so
would call it an
trivial.
extension
It's so
since we
trivial.
don't know. So, okay, Cecilia.
But there are no
Do we
gangsters.
know what the extension is yet?
No, but you
No,
are.
no.
But I'll tell you what happened, because these people, you know, they were tried to be economic, you know, all these. They were people, after all, we were told by 4 Nobel laureates that we had only, you know, we had the two-component neutrino theory. It was Salam, it was Li and Yang, it was Landau. If they said so,
That
it
was
should have been
50
right.
years ago.
I know, and then so when they started with the Standard Model, they just said, well, we for the right hand, for the neutrino, for everybody we put a left-handed component and right-handed. But for the neutrino, we don't have to put the right-handed, so we don't put it. So of course, any sensible person would put it. So I would not consider that to be an extension because there are no gauge forces, nothing. But anyway, I had another thing I wanted to say. I think this title, quantum mechanics, is very unfortunate that we call quantum mechanics. Because, you know, Max Planck, he nominated Albert Einstein to Nobel Prize twice because of his new mechanics. That was, of course, we don't call relativity new mechanics. You know, because mechanics in quantum mechanics has often nothing to do with mechanics. It's, you know, we just call it mechanics. I mean, so it can be anything, and it has no dynamics in it. So I'm glad you said over and over again that these are just quantum rules. Once you have a theory, you know what you're supposed to be doing. You have to have a Hilbert space, and you have to have, you know, you introduce your operators, and so you follow the rules, the superposition. If you do path integral, whatever, you follow all those rules. So it's unfortunate that we call it quantum mechanics as if it has some dynamics in it, but it doesn't. Maybe you should change that name. Thank you. Huh?
If I could change names, I'd change many names. Quantum mechanics, like most names in physics, are historically driven. I think it was either the three-man paper or Heisenberg. I'm not sure where, I think it was the three-man paper where that came in. Obviously, it was a copy of classical mechanics, which is the framework of classic Newtonian physics. Anyway, we're stuck with it, I'm afraid.
Other questions?
Gerard?
Yeah, you said there are no paradoxes in black holes according to string theory. Well,
No,
I
didn't say, I didn't.
You what?
I didn't. I said I hoped. My favorite solution to the paradoxes is what's called fuzzballs, which is what actually the explicit solutions that describe a class of black holes in string theory yields, which is a space-time in which the apparent horizon is not a horizon. Inside there's nothing. Space-time ends. There's kind of just like what you were describing, although not the same. So you come into a black hole, and you have a structure which you see near the black hole at some size of the bigger than the Planck length, but small, presumably, with of higher dimensional curved space, and you pull out. There's no inside. Looks like a black hole far away, behaves like a black hole for external observables, but there's no inside. Anyway, that describes certain black holes, and there's a class of string theorists who are trying to push that to describe within string theory all black holes. And that would be, to me, the most reasonable, satisfying solution. It would solve the paradoxes in a way that's different from what you're trying to do or what many other people are trying to do. But I did not say that there are no, I said that direction I hope works out.
Then rephrasing the question, would you think there are predictable observations? Suppose I gave you a black hole the size of a proton, then at least my theory gives you a very explicit prediction which would not come from Hawking's original theory, which is the entanglement of opposite sides, which would be observable experimentally.
Yes, no, I don't think that it would be different.
Yeah.
Definitely different.
Okay.
So I think we should stop now, but there is an announcement by we have, yeah, let's see. We should, well.
Something has happened here. I guess we will start again in half an hour, 15:45.